All right, it's the top of the hour here at AP Physics C, and we're going to study some simple harmonic motion. All right, let's make sure that my microphone works. I hope you all can hear me. Hello out there in COVID-19 land. This is AP Physics C Mechanics, and my name is John Frensley. I teach at Prosper High School in Prosper, Texas, about 30 miles north of Dallas. We're going to do some simple harmonic motion today. It would be great if you had something to write with and something to write on. If you're watching a live session, I would encourage you to try to kind of take everything in rather than frantically making notes. You can go back and watch the replays, and if you're watching this on a replay, feel free to pause, rewind, all that stuff. If I talk too fast or if you need to hear something again, that's a good technique right there. All right, start with a warm-up. I'm going to call it a go to it. We've got a cart, it's mass M. It's attached to a spring constant K. Let's let X equals 0 be the equilibrium. That's where the spring has no stretch or compression. But what I want you to do is consider the cart when it's not at X equals 0, but it's some other X, which we're just going to call X. Okay, there you go. I want you to do two things. You're going to write a Newton's second law equation. You're going to relate the acceleration to those three letters that are up there in the paragraph. And then I want you to take that Newton's second law equation, rewrite it as a differential equation that relates position and time. I'm going to give you 2 minutes to take a stab at this. And on your mark, get set. All right, we will answer these later on in our discussion today. Now, just so you know, from starting now, this is going to be a little bit P1 friendly. So if you're from P1, I'm going to tell you when it's not going to be friendly to you anymore, but this stuff is friendly for you. All right, so let's talk the overview here. We're going to discuss the difference between periodic motion and simple harmonic motion. Then we're going to figure out what makes simple harmonic motion so simple. What are the properties that make it so great and easy, easier than it could be, right? We're going to determine whether a motion we're looking at is simple harmonic motion, right, by looking for the properties or a lack thereof. And then we're going to write a differential equation, that's not the P1 friendly part, for a system undergoing simple harmonic motion. And then we're going to use that differential equation to figure out the period of the simple harmonic motion. All right, so here's what you need to know. First of all, this word, oscillation, scary word, Wouldn't want to meet it in a dark alley in a spelling bee. It means a motion that repeats back and forth between two endpoints. So I got an example here. You can hopefully see the bouncing rubber ball there. You can see it has an mg force acting on it. Then when it hits the ground, it's got a humongous force normal. That's what kills you, by the way, when you jump out of a building. It ain't the mg that kills you. It's the big force normal at the bottom, right? So equilibrium is the point in the oscillation where the two forces balance. It happens right about here. You can see that there's a specific moment. I hope you're seeing my mouse cursor, where the mg and the force normal are the same length. All right, that's when the equilibrium is. And then the endpoints are where the object stops and reverses. So for the bouncing ball, that's going to be where the ball's at the highest point and when it's the most squished. So hopefully you can kind of see the equilibrium there. That's when the normal and the mg balance out. That's equilibrium, balance forces. Now, simple harmonic motion is a special type of periodic motion. So I have my little Venn diagram down here that shows that all these repeating motions are periodic motion. Simple harmonic motion is a subset. It's a special type of periodic motion. It has 4 properties, all right? So here's simple harmonic motion. Property number 1, the net force has to be opposite the displacement from equilibrium and directly proportional to the displacement from equilibrium. So what do you mean when you say that? Well, if the force was in the same direction, let's say my nose is equilibrium, and then I offset from equilibrium, if the force is the same direction as displacement, then the object's going to leave and never come back, okay? It's kind of like me when I'm at a party and find out that somebody's coughing a lot, I leave and I never come back, okay? Now, if the force is opposite displacement from equilibrium, it's going to push the object back. It's going to push the object back. That's a repeating motion, right? But here's the key. The force has to be directly proportional to displacement. That means that if the displacement's doubled, the force is doubled, okay? Not any other function, like a linear function kind of thing, right? Now, the potential energy has to make like a quadratic function with the displacement from equilibrium. If this is sounding familiar, I'm hoping that you're thinking, force directly proportional to displacement. That's a spring, like F equals kx. X like to the 1 power, not like squared or radical or anything like that. Potential energy is 1/2 kx squared, like for a spring again, right? Let's see. If you make a graph of anything versus time for your simple harmonic motion, you're going to get a sinusoidal function, right? Not any other kind of repeating motion, but a sinusoid. Position, velocity, acceleration, momentum, force, anything you can think of versus time is a sinusoid. And then the last one, and this is the big one for simple harmonic motion. This is the really simple of simple harmonic motion, the period, which is the time it takes to go up and down one time or back and forth one time. The period does not depend on the amplitude. That's a key point in simple harmonic motion that makes it simple. Now, that's 4 different properties, but I have good news. And the good news is that they're all equivalent, which means if one's true, they're all true. If one's false, they're all false. So you're going to find them all 4 together or none of them together. So let's look at some things that are not simple harmonic motion. So we got a bouncing ball here, right? And you can see that I made a graph, the blue graph of force versus displacement. Displacement here is how high the ball is. And you'll see that that is not a direct proportion. It's not a line through the origin. So the force is not directly proportional to displacement. Why? Because the force versus displacement is not a line through the origin. Second of all, displacement versus time is not a sine type graph, sine, cosine, you know the type, right? This is a repeating set of parabolas. I know what you're thinking. Parabolas are simpler than sine waves, right? Not when they're repeating over and over again. Would you like to write a piecewise function with an infinite number of parabolas? I didn't think so. So this is a periodic motion. It is not a simple harmonic motion. Here's another thing you'll notice is that, and you can try this on your own with any bouncing ball you can find. Drop the ball from a low height, and it bounces very quickly. It has a short period. Drop the ball from a high height, takes a long time to bounce. The period definitely depends on the amplitude. The amplitude tells us the size of the oscillation, right? So the green has a high amplitude, the red has a low amplitude. We're going to define what amplitude is a little bit better later on, so don't you worry about that. Here's a cart that's just bouncing back and forth between 2 barriers. Maybe it's made out of some kind of perfect rubber or something like that. But guess what? Not simple harmonic motion. Well, let's look at the force versus displacement graph. It's not a line through the origin. Instead, you have no force at all until you get to the ends. I don't know if you can see this, but there's a really big force arrow that just shows up for an instant right when the cart gets to the ends. That's not a force directly proportional to displacement. That's some other kind of relationship. And the displacement versus time graph is not a sine wave. It's this triangle sawtooth type thing. You'll poke your eye out, right? Not simple harmonic motion, right? Not your friend. Now, can I tell you who does know the difference between not simple harmonic motion and yes simple harmonic motion? An infant, okay? So try this on an infant. Try rocking her with a motion like this one you see in the diagram where it's like jerk, 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 with these sudden jerks at the end. She's going to be pretty mad about it. And don't even get me started on this, okay? You're going to dribble your baby like a basketball. That ain't fun. She's going to be really mad at you, and guess what? So CPS. So you know what? We're going to do this when we rock our baby. Yeah, so we see the force is not proportional to displacement. The graph is not a sine wave, but you know what? This is the motion that your baby wants. I guarantee you, every baby bouncer, every baby swing, and every mother knows to slow down as you reach one end, speed up toward the middle, slow down as you reach one end, speed up toward the middle. This is a simple harmonic motion. We've got this cart. It's on a spring. Let's look at this force graph. The force is directly proportional to displacement. How do I know? Line through the origin. That's what directly proportional means. So if anybody ever says, hey, are these two things directly proportional? Check. Line through the origin, got to be both. Line through the origin. Now, let's have a discussion here. Why is the slope negative, Frensley? By the way, everyone calls me Frensley, not even Mr. Frensley. So I'll never get a PhD because I'll just still be Frensley, right? Okay, so why is the slope negative? Well, remember what I said, that the force has to have the opposite sign that displacement has. So look at the diagram up here. When the cart has a positive displacement over here on the right, the force is to the left. When the force is to the right, the cart has a negative displacement, right? So force and displacement are opposite signs. So positive displacement, you're to the right, force is negative to the left, you get the idea, all right? So that's one way we know it's simple harmonic motion. Remember, one property, all four properties. Here's a beautiful sine wave. Well, Frenzy, it's not a sine wave, that's a negative cosine wave. You know what, I don't care, okay? It's a sine wave, it's just been shifted, okay? So don't bother me with the details here. Yes, technically a negative cosine. Whether it's sine or cosine just depends on where you start, okay? Did you start carrying when it was at equilibrium? Then it's a sine wave. Did you start carrying when it was at an endpoint? Then it's cosine. By the way, the amplitude of this oscillation is 1 meter. Amplitude is like the radius of the oscillation. It's the distance from the center out to one end or the other. So 1 meter amplitude. Well, what if the amplitude changes, Frensley? All right, so there's my little signal. The force versus displacement graph is a straight line through the origin, directly proportional, comes from F equals negative kx. And we have our sine wave for displacement versus time. All right, now all of my lab equipment has been put into quarantine, okay? So I can't show you this with real stuff, so you're just gonna have to believe me, maybe try it on your own. Put an object on a spring and wiggle it back and forth a little, wiggle it back and forth a lot, it'll have the same period. The period does not depend on the amplitude. That's an important feature of simple harmonic motion. The period doesn't depend on the amplitude. All right, so we see that there. Here's another thing with simple harmonic motion is what's called a simple pendulum, all right? Now, what makes a simple pendulum simple? All the mass is dense, and all the mass is basically the same distance from this point up here called the pivot point right there. So, you know, a small, dense object, all the bob's mass, we call it a bob, is all the same distance from the pivot, and the mass of the string itself is negligible. I have a graph here of what's called tangential force. If you look carefully, these two red force vectors, one is the tension force and one is the mg force. Well, these two forces partially cancel, and the only force that doesn't cancel, that really matters for this motion, is this blue component you see I'm trying to point to. That's actually the mg sine theta component. It's kind of like the downhill force on an incline. Well, that light blue component, that's what's making the bob oscillate back and forth. And if I make a graph of just that light blue component force, because all the other components cancel, then I get a line through the origin, which is negative because the force points left when the bob's displaced right. The force points to the right when the bob is displaced left or whatever. Okay, so and then we have the displacement versus time. For a pendulum, we usually say displacement isn't the number of degrees it is from the equilibrium, which is 0. So you could do it in meters if you want to, but most be like 5, 10, 15 degrees kind of thing. So this thing seems to have an amplitude of about, I don't know, 14 degrees, let's say. And so that's its angle versus time as a sine wave. Okay, so all good. So to review, we see force versus x is a line, negative slope to show that force and displacement are opposite directions. We got our sine wave here for displacement versus time. And then, and you're gonna have to try this on your own, and you can try this on anything. Do you have keys on a lanyard? Here, pull out your keys on a lanyard right now and just make them wiggle a little bit and then make them wiggle a lot, and they should have the exact same period. So 3 pendulums, all the same length, all the same bob, should have the same period regardless of their amplitude. All right, there's simple harmonic motion. All right, if you're watching and you're from P1, this is the part where it's going to get not very friendly for you, because now when we talk about AP Physics C level simple harmonic motion, we need to be able to analyze simple harmonic motion in terms of what's called a differential equation. So all simple harmonic motions, the two you just saw and two others that I'm going to show you here in a moment, can be written as a differential equation. All the differential equations have the same form. What do you mean they have the same form? Well, let's look at what that form looks like. Okay. Oh my gosh, it's calculus. Somebody do something. Okay. I'd rather have the COVID-19, right? No, it's really not that bad. Okay. So let's have a look here. What do we got? What does that look like to you? That looks like acceleration. It's the second derivative position, right? So I'm just looking at acceleration. No big deal. And then this is just position. That's just your displacement from equilibrium. So this isn't so bad. It looks like acceleration is equal to something with displacement in it, right? No big deal. So I'm going to break it down. So I'm going to take the same equation. I'm going to break it into pieces. Let's see what we're looking at. We're looking at some sort of acceleration. Let me warn you, this could be a linear acceleration, second derivative of x with respect to time, or it could be an angular acceleration. That means second derivative of theta with respect to time. It could be that too. But if this is second derivative of theta with respect to time, then you got to have a theta right here. So that's why I say some sort of acceleration. Is it meters per second squared? Then this got to be meters. Is this radians per second squared? This has got to be radians. What's this thing right here? What's this W? It's actually the Greek letter omega. It's the lowercase version of omega. And really the only point of this is that there needs to be something here that is negative. So how do I know for sure that this is negative? I take a number, I square it, so I know it's positive. I slap a negative on it. So I know for sure this is negative. This has got to be negative. That is non-negotiable. So when we have a simple harmonic motion, what we're looking for is an acceleration equal to a negative bunch of constants times something that's position. If this is a linear acceleration, this is regular old meters position. If this is an angular acceleration, this is theta, like with radians, negative constant front. So let's see what this looks like when we put it into practice. Okay, first of all, I want to say this. When you have a differential equation is solved, but it's solved by a function, whereas a regular algebraic equation like x squared minus 2x plus 1 equals 0, that's solved by numbers. Differential equation is solved by functions. So what function solves this differential equation? Well, this one, of course, x equals a, which is called the amplitude, sine or cosine, doesn't matter which one you choose, they both work, omega t plus phi. So what are these things that I'm looking at? Well, x is where the object is at a certain time. Just where is it, right? T is the time that you're asking about. So if you're like, hey, where's the object going to be at 6.7 seconds? Plug in 6.7 for the time. A is the amplitude of the motion. Omega is called angular frequency. We'll learn about that later. And then phi is called the phase shift. It takes the graph and it shifts it left and right. And all that means is that you started your time equals 0 at a really awkward moment. You don't need a phi if time equals 0 is when the object's at an endpoint or when the object's at equilibrium. You only need phi if you start time equals 0 at some in between the endpoint and equilibrium. Let's try to avoid that. It makes me sad, okay? I want to prove to you now that this equation solves this differential equation. So how do I know that this function solves this differential equation? Simple. You just plug in and see if both sides are the same, just like in algebra, okay? Is x equals 1 a solution to x squared minus 2x plus 1? Just plug in x equals 1 and see if you get both sides be the same. So here it comes. I'm going to prove it to you. I'm going to take x equals a cosine omega t plus phi, and I'm going to plug it into this differential equation, see if I get the same thing on both sides. Okay, well, how do you plug into a differential equation? Well, it says here, take the second derivative, so I'm going to do that. I'm going to take the second derivative. So take one derivative of this x, you get velocity. Take the derivative cosine is negative sine, pull out an omega. All right, that's chain rule. Let's take another derivative for the second derivative, right? Another derivative gets us acceleration, so negative sine becomes negative cosine, pulls out another omega from the chain rule. Okay, so now I'm going to take this right here, and I'm going to plug it in where this used to be. I'm going to plug the second derivative into the second derivative. Let's have a look. So I'm going to look at the last equation right here. If you look, I have d squared x over dt squared is negative omega squared a cosine omega t plus phi. But a cosine omega t plus phi, that's the same thing as this x. So I get second derivative equals negative omega squared times x. That's this equation. So x equals a cosine omega t plus phi is the solution of this differential equation. It's the function that makes both sides say the same thing. Okay, so therefore, the second derivative of x is negative omega squared x. The function makes the differential equation a true statement. Okay, why do we care about the differential equation? Okay, it's a bunch of calculus. There's only one reason we care. There's only one reason we care, and that is because if we use the differential equation, what we're going to do is we're going to write the differential equation, we're going to pull out that omega, and that's all we're going to do. We're just going to pull out the omega. We're not going to do any more calculus, okay? Write the differential equation, pull out the omega. Then, once we have the omega, we're going to set that omega equal to 2 pi over the period, because that's what omega is. It's 2 pi over the period, right? And we can solve for the period. So what we're going to do is we're going to take the differential, we're going to write the differential equation, we're going to pull out omega and throw the rest of that calculus looking stuff away, set the omega equal to 2 pi over the period, and find out what the period of our system is. Here's how it's going to work. Get ready. We're going to do it with the spring and mass. Here's how it works with the spring and mass. Okay, step one. We're going to write a Newton's second law equation for this system. This was the warm-up, right? I showed you the system and I said, please write a Newton's second law equation. So that's net force equals ma. Well, the net force of a spring is kx, but we got to put a negative on it for the direction. So the negative here is just to say that the x and the acceleration are in opposite directions. The force and the displacement point opposite ways. Displace right, force left, displace left, force right, right? Okay, so step one, Newton's second law equation. Step two, get the acceleration by itself, and then change the acceleration into the second derivative. So how am I going to get the acceleration by itself? Divide by mass. Just going to divide by mass. Okay, just the m goes underneath. Not that big a deal. Oh my gosh, here it is right here. It's a, it's just negative kx over m. All right, no big deal. Not that bad yet. It's just algebra 1 stuff, right? Now, now this is not algebra 1. This is a second derivative now. Now it looks like we're going to do calculus, but we're not actually going to do calculus. We're not going to take any derivatives or integrals. All I'm going to do on step 3 is say, what is omega? Well, let's see here. We have second derivative of position equals negative this thing times x, and we said that the simple harmonic motion differential equation is second derivative equals negative omega squared times x. So this specific system of the spring and the mass is second derivative equals negative k over m times x. All simple harmonic motions are second derivative equals negative omega squared x. So guess what that means? That means omega squared is the same as k over m for this system. So omega squared is k over m for this system. Step 4, set omega equal to 2 pi over the period and solve and see what you get. So here I go. Omega squared is k over m. Let's take the square root. Nothing scary yet. Ooh, now we're going to say that omega is 2 pi over the period. Oh, that's the definition of omega. Omega is 2 pi over the period. That's all omega ever is. So now we're going to flip both sides. All right, that flip under the radical and flip the 2 pi over the period. There's the t. Oh man, I know you can tell where we're going. We're about to solve for t. And if you've studied simple harmonic motion before, oh, there it is. T equals 2 pi radical m over k. So that's the process for figuring out the period of a simple harmonic oscillator. You write a Newton's second law equation, make it look like the differential equation, pull out the omega squared, square root it, and then solve for the period. All right, so I'm going to let you try this now. Okay, this is going to be some guided practice. I want you to look at this. This is called a torsion pendulum. Now, this blue disc has a rotational inertia I, and it's attached to this kind of rod. Imagine this rod is like a really long eraser, right? Okay, and it's going to flex. Can you see it flexing as it rotates, right? Well, it turns out that the rod applies a torque, that's the letter tau, negative beta theta. Theta is the angle that this thing is rotating. If you look, its amplitude is pi over 2 because it rotates 90 degrees in both directions. So theta goes as big as pi over 2 and negative pi over 2. Beta is like a spring constant. It just depends on the rod. Okay, it's a property of the rod. Okay, the torque is negative because if you rotate one way, then the torque pushes you the other way. If you rotate counterclockwise, the torque is clockwise. You get the idea, right? Okay, so that's the idea there. So what am I going to ask you to do? What I'm going to ask you to do is I want you to go through the steps. I'm going to give you some time to go through the steps. All right. So what you're going to do is you're going to first write a Newton's second law equation. I'll bet you it ain't going to be F equals ma because we're looking at a torque here, right? Then you're going to solve for acceleration, but it's probably not going to be meters per second squared. Acceleration might be that other one. And then rewrite it as a d squared theta over dt squared. What's your omega? It's going to be the constants between the negative sign and the theta. You're gonna have, that's going to be omega squared. So then you're going to set it equal to 2 pi over the period, and you're going to solve for the period in terms of I and beta. When you're done, your period will have a square root and an I and a beta, and probably a couple of constants in it, right? Some very familiar ones. All right, so I'm going to give you 5 minutes to try it out and get ready for some fun background music. On your mark, get set, go. All right, back to me. Okay, let's have a look at how we can apply these steps here. Okay, so write Newton's second law. Well, we know that we were told that the torsion pendulum, the torque is negative beta, a constant times theta, angle that the disc is rotated through. We also know torque equals I alpha. That's Newton's second law for rotation, right? So there's your acceleration right there, except it looks like an alpha instead of an A. Let's get that alpha by himself. Okay, so we're going to get the alpha by himself. All right, there we go. Alpha's by himself. We've got negative beta, a constant for the chord, over I, a constant for the disc, times theta. What's the simple harmonic motion differential equation? Well, it doesn't have an acceleration. It has second derivative. In this case, second derivative of angle rather than second derivative of x, which is like meters, right? Okay, so we have second derivative of theta with respect to time, kind of like second derivative of x with respect to time. We have a negative, kind of like a negative. We have beta over I, which is a constant, okay, and theta, which is like position, yeah? So that means that the omega squared is just the beta over I. So see, we're not doing any real calculus. We're going to throw this garbage away, throw away that junk. We're just going to take the beta over I and say that it's omega squared, all right? That's step 4, right? So really the hardest thing to do is just figure out what your omega squared is. You start with Newton's second law, get alpha by itself, and the constants are omega squared. So omega squared is just beta over I. And then I'm going to take the square root because I don't like squares. Okay, all good. And then let's have a look. 2 pi over the period. That's beta's 2 pi over the period. So let's flip both those suckers right there. Oh, there you go. These two guys are still in jail. They can change bunks, but they're still in the jailhouse. Let's flip that 2 pi up. And you got your periods 2 pi radical I over beta. That's a torsion pendulum right there. Hey, Friendly, isn't I kind of like mass? And beta's like how springy the cord is, right? So isn't that kind of like M over K? Sure is, Sherlock. So you see, you didn't even have to go through that whole process. You could just say, hey, I is like mass and beta is like how elastic the K of the spring is, and just go to town, right? All right, now this process becomes a little bit more difficult when we talk about a pendulum. Let me tell you why. So let's have a look at this pendulum situation. So I want you to pretend like the mass is M and the distance from the center of the bob to the pivot is L. A lot of people think that L is the length of the string. It's actually the distance from this clampy point up here to the center of mass of the bob. That's important to know, okay? Now, the net force is mg sine theta. So when this thing is like at theta equals 45, then the mg sine 45 is it's like the downhill force on an incline, right? It's just instead of force normal in mg, it's force tension in mg. It's the same idea, okay? What's the difference between a t and an n anyway, right? So mg sine theta is the force that's trying to push the bob back to equilibrium. Now, I'm going to treat this as if it's a rotational situation. Okay, this is how I'm going to get the period of the pendulum. I'm going to treat this like rotation. So I'm going to do like with torques. Okay, so here's what I'm thinking in my mind. I'm thinking that the net torque is mg sine theta, which is the force, times the length, kind of like the radius, like torque equals radius times force, right? So here's the force, mg sine theta. Here's the radius to where the force is applied, L, and the blue arrow, which is the mg sine theta, and the radius vector are perpendicular. So I don't need another sine theta. One is enough. Thank you so much. Okay. Negative because the force is to the right when the bob's to the left, and the force is to the left when the bob's to the right. You get the idea. All right. Now I'm going to set that torque equal to I times alpha because that's what torque equals. But what's the I of this situation? What's the rotational inertia when all of your atoms are the same distance from the pivot? That's right. It's just mass times length squared. It's 1. There's no other weird constant in front. So the rotational inertia is just ml squared. That's what makes the simple pendulum simple, because all the mass is the same distance from the pivot. I equals ml squared. And we can be happy with that. Okay, good. All right, so let's set this garbage equal to each other. All right, so here we go. That's I times alpha. You see at the bottom there? I times alpha, the I is ml squared, equals, and that's the torque. So that's just torque equals I alpha. Okay, so what am I going to do? I'm going to do what my steps say I should do. Newton's second law, get the A by itself, alpha in this case, and make it a differential equation. Let's get that alpha by itself. We're going to nuke A and L, and we're going to nuke the M's, so the mass of the bob doesn't matter. That sounds familiar to me from a pendulum, right? The mass doesn't matter. Ooh, I get my alpha equals negative G over L times sine theta. Okay, now let's change that into a differential equation. Oh, there it is. There's a second derivative of theta. There it is, yay. And let's compare that to our simple harmonic motion differential equation. Oh no. Well, let's see. It feels like there's something kind of off here. We got the second derivative. Okay, the second derivative. Okay, that works. Okay. Here's a constant. I got a constant right there. Okay. I got my x. I got sine theta. Wait a minute. This isn't supposed to be sine theta. This is just supposed to be regular garden variety theta. This is theta's inside of a sine. That's bad. That's not simple harmonic motion. You can't say simple harmonic motion if your position is inside a sine, cosine, tangent, log, e, square root, or any other nightmare that you can dredge up out of your pre-cal class. The theta or the x has to be alone by itself, not inside of something. But there's a fix for this. And the fix for this is this. We can change the sine theta into regular theta if we apply something called the small angle approximation. Now, here's a small angle approximation. If you don't believe me, pull out your calculator and set it to radians. In radians, which is what we only do calculus in, sine theta is almost the same as theta in radians. Like, try this. Do sine of 0.1 in your calculator in radians, and you're going to get 0.0999 is almost the same as 0.1. Try sine of 0.2. You're going to get a number that's almost the same as 0.2. Try sine of 0.3, but the higher you go, the less like each other those two numbers are going to be. So if you try the sine of 67, you ain't going to get anything near 67. Okay, that's too big. So if the angle stays small, and my rule of thumb is like 20 degrees, okay, I know I'm switching between degrees and radians. Deal with it, okay? But if you stay less than 20 degrees, then sine theta and theta in radians have about a 2% difference maximum, 2% error, which makes me feel okay, right? You know what? That's just okay with me. So what does that mean we're going to do? What we're going to do is we're going to change sine theta into just theta, but we have to say theta stays small. So the simple pendulum can only have small oscillations. It can't swing out like a kid trying to go over the bar, okay? Just very small, okay? Now, once I do this, then I can say, oh, second derivative, there it is. Here's my position variable without the sine, because sine and theta and sine theta are almost the same. But here's my omega squared. Omega squared is G over L. So if omega squared is G over L, okay, let's all sing it together now. Omega is radical G over L. Come on, I want to be able to hear you now. Okay, that means 2 pi over the period is G over L. So we're going to flip both sides, and then we're going to solve, and oh my gosh, it's T equals 2 pi radical L over G. That's where this stuff comes from. It comes from the simple harmonic motion differential equation. So all you got to do, Newton's second law, get acceleration by itself, rewrite it as a second derivative, and write the simple harmonic motion differential equation underneath it. Here's the simple harmonic motion differential equation, and just pull out the omega squared. It's like eating an apple. You don't eat the whole thing, like the core and the seeds and stuff. You eat the good stuff, you throw the rest away. This is the good stuff. The G over L is omega squared, or the K over M is omega squared, or the beta over I is omega squared. That's what we want. Just get the beta, the omega squared. If you get the omega squared, it's all downhill from there. Okay, so once again, you cannot do simple harmonic motion with this big wide swing. Look at the tangential force versus angle graph. Man, it looked like it was a line when the angle was small. That's what we wanted. Force versus displacement's a line, but not if you swing way out into the boonies, man. If you're swinging all the way up and trying to go over the bar like the Mythbusters, then this is not a simple harmonic motion anymore. And you might be fooled into thinking this is a sine wave, but this sine wave, if you actually like plot it out, it's actually flattened at the top, okay? So that's like, you know, it's kind of like Matt Damon's head, okay? It's flattened at the top. That's not a sine wave. It's not truly a sine wave. The unsuspecting eye might believe that it is, but it's not. So if you try to do like period equals 2 pi radical L over G for this big long swing, the equation will give you a different number than Mother Nature, and that means our physics is not right. So our physics for pendulum only works near, you know, equilibrium. Don't go more than 20 degrees. Okay, well, if there's a simple pendulum, there has to be a not simple pendulum, right? It's called a physical pendulum. And you can already tell what a physical pendulum is. It's the thing where the mass is not all the same distance from the pivot. Here, we have some mass close, medium, far from the pivot, all right? So we call that an extended body. Atoms are all different distances away. Well, it is simple harmonic motion because we got our force versus angle, or force versus displacement is just a straight line through the origin. We've got our sine wave. You can try it on your own. Okay, you can build a simple pendulum, physical pendulum out of anything. I don't have anything within reach here, but if you could just find like a pencil and something with a hole in it, like for example, a ruler that just has a hole in it, right? Then you can make your physical pendulum and try different amplitudes, and you'll see that the timing, the period is the same. Simple harmonic motion, right? All right, here's your last guided practice for the day. This is it. The bar's mass is M. The distance from the pivot to the center mass is going to be D. That's the distance from the pivot to the center mass. And the rotational inertia is going to be called I subscript D. Remember, the rotational inertia depends on where you pin down the object. So in this case, this rotational inertia depends on where this axis is. So we just call it I subscript D to say that's the rotational inertia when you pin down a distance D from the center of mass. Now, I'm going to remind you, it's just like this part is just like for the simple pendulum. The component of the weight force that is tangent to the path of the center of mass is mg sine theta. So the center of mass is D away, and the force that doesn't cancel out is mg sine theta. So mg sine theta is the force that is actually the net force on the center of mass. All the other forces balance out. We don't care about them. Here's your task. You're going to derive an expression for the period of the physical pendulum in terms of the I and the mass and the D and gravity. You got to write Newton's second law. Okay, it's going to be a torque equals I alpha law. But what is the torque? I gave you the force, and force is just torque is just force times the distance. I wonder what that distance could be. So then you're going to write a Newton's second law that involves torque and alpha. You're going to solve for the alpha. You're going to rewrite it as d squared theta over dt squared. You're going to see a sine theta, but you're going to change it into a theta. You're going to pull out the omega squared and throw the rest of that junk away, and then square root it and set it equal to 2 pi over the period. And you're going to solve for period. All right, you ready? Think you can do it? Okay, good luck. All right, I hope that was as much fun for you as it was for me. All right, step one, Newton's second law. It's going to be torque. It's going to be torque, which is force times distance. So torque equals I alpha. The torque is the force, mg sine theta, times the distance at which that force acts, which is the d, distance from the pivot to the center mass of the bar. So there's your torque. Negative, because the force points that way when the bar is displaced the opposite way. All right, there's your I times alpha. Step two, get the alpha by itself. So there's the alpha. I grouped all the constants together. I will let you guess why. Sine theta. The negative is there too. The negative needs to be there, all right? Okay, differential equation. Alpha is the second derivative of theta. So I've got my second derivative of theta. I've got my constant that I want that to be my omega squared, but I wish I just had a theta right here. So I said this is step 2.5 here. We're going to say as long as you keep the theta small, then sine theta gets to be just theta. Sine theta gets to be just theta. So here's my differential equation. Second derivative of theta is negative big constant times just theta. Well, second derivative equals negative big constant times just theta. That looks like the simple harmonic motion differential equation. Second derivative equals negative. The big constant is omega squared, and theta is like x. It's the position variable, right? So let's just set this whole big piece of junk equal to omega squared. So there's my omega squared equals mgd over id. I'm not even consistent with capital and lowercase letters. Please, when you do the AP exam, be consistent between whether it's capital or lowercase m, okay, or whatever other letter you're using. All right, square root. Let's sing this song again. 2 pi over the period. Flip both sides. That's the period of a physical pendulum. All right, so we studied 4 different simple harmonic systems today. We looked at a spring and mass, we looked at a torsion pendulum, we looked at a simple pendulum, and we looked at what's called a physical pendulum. Feel free, if you would like to watch this again, rewind and see all the good stuff. But what we really need to know is that simple harmonic motion has 4 special properties that are all equivalent. You got one, you got them all. You're missing one, you're missing them all. That's simple harmonic motion. Any simple harmonic motion system can be written in the form of acceleration equals negative a constant times position. So acceleration is directly proportional to position and has the opposite direction. Omega is 2 pi over the period. And if acceleration depends on sine x or sine theta, you get to say that sine x is the same as x, sine theta is the same as theta, if you keep that theta small. 20 degrees, whatever that is in radians, I don't even know. All right, that's the end. I hope you enjoyed my video. You can like me on Facebook, look for Friendly AP Physics and the Aperture logo, and I'm going to play out with my outro. On your mark, get set, have a good one. I'll see you tomorrow. Tomorrow's lesson is going to be very P1 friendly, so tell your friends in P1 that tomorrow's going to be for them too.